presentation to you. Good morning, friends. So today, on this fifth day, we have this second session, and even this is the last session of your FDP. So welcome in the last session again. And in this session, we have with us Mr. Jayant Lakhlani. Sir is founder of the firm Lakhlani Associates. Had passion for structural engineering since his college days at undergraduate level. After completing his post-graduation in computer-aided structural analysis and design from Gujarat University, India, he got experience with one of the best structural designing firm in the industry. Sir was felicitated by the National Award for Excellence in Structural Engineering in competition held by India chapter of American Concrete Institute for the year 2005. His area of interest includes development of unconventional structural system and innovative use of structural materials. Sir is having specialty in his to provide top-notch quality civil and structural design and drafting services at global level while adhering to the project time frame. So I know Sir since last 18 years. He is very good innovator, I can say, in the field of structural engineering. He has developed many structures who are unique in their even Sir is a really good guide. So he is guiding many dissertation, PG dissertation in Marwadi University also. So in this session, I welcome Jayant Sir on behalf of Marwadi Education Foundation and Academy AICT for, and I am very much thankful for sparing his time and giving the positive node for conducting this session. So I am sure that this session is going to be most interesting session for all the participants. And with this, I hand over the session to Sir. Sir, please.
Thank you, Tarak. Thank you for your kind words. Good morning, friends. As Tarak said, I am Jayant Lakhlani, Principal and Chief Structural Designer of Lakhlani Associates. Ours is a civil and structural designing firm, and we are in the field since almost last 30 years. So first of all, I would like to congratulate Dr. Tarak Vora and his team for organizing such an excellent event of faculty development program, which brings the industry and academics together and helps to bridge the gap between industry and the academics, and also providing a beautiful platform for knowledge sharing. And this online, the possibility of conducting this kind of events online has helped a lot to bring the people from all over the world together. So, Tarak, how do I share my screen?
Sir, there is green tab, share screen.
Okay.
That you have to click, and then you have to select the window of presentation.
Okay.
Yes.
Can you see my screen?
Yes. Screen is visible.
Okay. So, friends, our today's presentation is on earthquake-resistant concrete buildings, collective efforts. So, normally it is believed that earthquake-resistant building is a liability of a structural engineer alone, but that is not true. Because you see, during the this design conception, designing and construction of any of the building, there are various stakeholders involved in the entire process, like architect, then structural engineer, site supervisor, contractor, and of course the local authority. So if positive attribution is not obtained from all of these stakeholders towards the earthquake resistance of the building, it is very difficult for a structural engineer alone to achieve that particular goal of an earthquake resistant concrete buildings. So in today's this presentation, we will discuss that what role each and every stakeholder has to play in achieving this goal of making a building earthquake resistant. Uh, but without going into the detailed mathematics of earthquake engineering and the earthquake resistant design, we will just focus on the at the conceptual level that what should be done by each and every stakeholder. So in today's this presentation, as the title is Earthquake Resistant Concrete Buildings, Collective Efforts. So we are going to discuss this earthquake resistant building and not the earthquake proof building, because there is a vast difference between these two. Because a earthquake proof building is a building which will not get damaged at all when it is subjected to the design earthquake. While in case of an earthquake resistant building, when we are talking about earthquake resistant building can get damaged up to certain level when it is subjected to a strong earthquake. But the philosophy is that it should not collapse. So world over, this philosophy of earthquake resistant building has been adopted by various design standards of different countries. And earthquake proof buildings are rarely built, and it is generally for the very important buildings like nuclear power station and such kind of buildings, because earthquake proof building will be too robust and it will be very expensive. And in, as I said, in earthquake resistant building, during so strong earthquake it may get damaged severely, but it should not collapse. Thus the safety of people and content is assured. So our goal is to design and build an earthquake resistant building and not the earthquake proof building. Secondly, we will focus our this discussion on buildings only. No other types of structures shall be included in this presentation. And as far as material is concerned, we shall limit our discussion to concrete only. And by collective efforts, as I said, it should be the joint efforts by architect, structural engineer, site supervisor, contractor, and the local authority. So before we enter into the discussion of various roles to be played by various stakeholders, let us have a look at some of the figures from the past history of the earthquakes. So these are some figures from history of earthquakes in the US. Here you can see that for majority of the earthquake, the death toll is in single unit only. For few, it is in double digits, and only for one case, that is the 1964 Alaska earthquake, it is in 3 digits. This is the history of earthquake in Japan. Here also you can see that, of course, the death toll is more than what we saw for the US, but here you can see that the majority of the earthquakes are 7 and above, so very strong earthquakes. So here also we can see that the death toll is say in 4 digits. Now let us see the history of earthquakes in India. Now here you can see that comparatively the death toll is very high as compared to what we saw for US and Japan, because US and Japan are the most earthquake prone areas of the world. So when we compare to those countries, we can see that the death toll during the earthquake in our country is very high. Why it is so? Now we see that during an earthquake, it is not the earthquake that kills people. It is falling buildings that kill them. So there is something wrong with the buildings that we are designing and that we are building as compared to other countries, that is causing such kind of high tolls during an earthquake. So we should first understand that what are the effects of earthquake on our buildings that require special efforts to make those buildings earthquake resistant, right? So once we understand those effects, then we can have this methods and steps to mitigate those effects and achieve a earthquake resistant building. So before we understand those effects, I would like to share one very interesting case that happened during my career a few years back. One of my client came to me with this picture, and he was about to build his own residence. So, and I was the structural designer for that residence of him. So he came with this picture, and he told me that I want to build my house like this, 1 feet above the ground. So I looked at him and I said, sorry, gentlemen, but I have not been taught how to build a building 1 feet above the ground. So he stared at me and said, okay, if you cannot make it 1 feet, let us make it 6 inches. But I want it like this. So then I asked him, have you heard about Newton? So he said, oh yeah, it was a very beautiful movie and Rajkumar Rao was very fantastic in that movie. Then I said, I am not talking about Newton movie. I am talking about Sir Isaac Newton, a famous scientist. He said, no, I have not heard about him. Then I said, okay, never mind. If you have not heard about him, even then, the law of gravity that was specified by him, it prevails. So, as far as the gravity is concerned, so jokes apart, as far as the gravity is concerned, we know that it is an ever occurring force. So whenever we try to play with the gravity, it will bring us to the ground, right? So we never dare to build a building which is above the ground. We always keep our building connected with the ground. Why? Because we know that there is some force existing which will pull our building down once we try to keep it in the air. So likewise, as the gravity is the commonly experienced phenomena, we all obey those phenomena and we build our buildings accordingly, that it is properly anchored with the ground and all the gravitational forces are properly distributed on the ground to keep our building safe. So same way, when we talk about earthquake, we need to understand that what happens during an earthquake and what kind of forces occur on our building, that we should understand and we should take care in our design and in our detailing, in our construction at every step. So very simply said, during an earthquake, the building experiences an horizontal thrust. How come so? So this example is very simple. Suppose we are standing on a bus which is at rest, and all of a sudden, if that bus starts moving forward, then it is all of our experience that we will experience a backward thrust. And if we have not hold to something, we might fall down backward side. So same way, when the building is at rest and all of a sudden when the earthquake occurs, the ground below the building moves in one direction. And due to the inertia of the building, mass inertia of the building experiences a horizontal thrust in the opposite direction. So due to this, and now we know that this inertia force is proportionate to the mass of the building. And it is nothing but mass into acceleration. Acceleration of the ground multiplied by the mass of the building, that is the horizontal force that the building will experience. So here you can see that for the building, the majority of the mass is located at each and every floor level. So each and every floor will experience a horizontal thrust, and that movement of that floor will occur in the horizontal direction. And once this is understood, we need to make provision for this kind of movement, though it might occur during once, maybe in the lifespan of the building, or it might never happen during lifespan of the building, but we need to make provision for such kind of forces as we make provisions for the gravitational forces to make our building earthquake resistant. So the first effect is the horizontal thrust that a building experiences during an earthquake. Next is the twisting of the building. Now, as such, there is no apparent this torsional moment or rotational, the moment is exerted on the building during an earthquake. During an earthquake, the building will experience the horizontal thrust only. But due to property of the building and unsymmetrical distribution of mass or stiffness, it might experience a twisting effect. So how this will happen? Tarak, can you see my mouse? Hello. Here,
Yes, sir, it is visible.
yeah, okay. Now here we see that suppose for this building, due to earthquake, this earthquake ground shaking is in this direction. The building will experience horizontal thrust in this horizontal direction. Now, suppose this is a very heavily loaded part of the building and this part is lightly loaded. So mass of this portion is more than the mass of this left hand side portion. So what will happen that the horizontal thrust experienced by this particular portion shall be more than the remaining portion because the force is equivalent to mass into acceleration. So here the mass is more, so the horizontal force is more compared to this portion. So this unbalanced horizontal force will create this kind of twisting effect in the building. Similarly, if let us say see an example of building with an unequal column height. So here what will happen that these columns are very long as compared to these columns. So this part is more stiff as compared to this part. So there is a unsymmetry in the stiffness of the building. So this is flexible portion and this is a stiff portion. So when the horizontal thrust is exerted, this stiff portion will move less as compared to this flexible portion. So due to that, there shall be a rotational movement of the building. Here also, if the unsymmetrical walls are there, that will also result into unsymmetry of the stiffness of the building. This stiff wall will resist the movement of the building, resulting into this kind of twisting moment. Similarly, here also, the wall will try to resist the moment and it will result into rotation of the building. Here we can see that there is an open parking in certain part of the ground floor. So this is a flexible portion as compared to this one, which is a stiff one. So stiff one will resist the moment as compared to the flexible one, and the building will experience the twisting of buildings. So these two are the main effects on the building: horizontal thrust and twisting, which we need to take care in our design, detailing, execution at each level. So before we further understand that how each and every stakeholder shall take care of this particular phenomena, let us have a look at if these forces are not being taken care of in the design and execution, what can be the result. These are the few of the photographs from 2001 Gujarat earthquake. Here we can see, and later on we will see that due to what this lack of detailing or lack of particular characteristics, this kind of the building collapsed in this manner. Here we can see that this open ground floor parking was there and the complete open parking has gone. Here also this open ground floor failure. In this failure of the column in open parking, here also we can see that the failure of column in open parking area. Here this was a U-shaped building, heavily damaged at the corner, and one wing of the building is totally gone. Here this is a L-shaped building, heavily damaged at the corner. Here also, certain part, this was open parking, this was having a ground floor, this construction, and the open parking area is gone. This was also an L-shaped building and one wing is totally gone. This is a pancake type failure of the building. Here the heavy mass located above the building, the water tank has gone. In this building, these two wings were connected by the staircase over here. So we can see that the complete staircase and one wing has gone. So basically it was a H-shaped building, English letter H. Here we can see that this only this lift shaft RCC course is standing and the remaining building has gone due to the lack of proper connectivity with the stiff this shaft of the remaining part of the building. Here also the open ground floor parking has gone. This is the complete overturning of the building due to the horizontal thrust. So now let us see that when we talk about collective efforts, what kind of efforts are required from each and every individual associated with the building design, construction and erection procedure. So first let us talk about the architectural features, right? So as far as architectural features of the building are concerned, overall shape, size and geometry of the building are very vital. If at the planning stage itself, it has been ensured that the features which are not favorable to achieve an earthquake resistant designs are avoided and a good configuration is chosen, then it will make easier for a structural engineer to achieve the goal. Now, the importance of geometrical configuration of building was very well stated by late Henry Dizenkow, a noted earthquake engineer of USA. He said, if we have a poor configurations to start with, all the structural engineer can do is to provide a band-aid, improve a basically poor solution as best as he can. Conversely, if we start off with a good configuration and reasonable framing system, even a poor structural engineer cannot harm its ultimate performance too much. So this emphasizes the importance of the configuration. If the configuration and the framing system is good, then you need not go for the this very meticulous mathematical calculation, calculating all the forces for 3 digits after this points and all those things. Just focus on how the building is going to perform or behave during an earthquake. Whether we are having a proper framing system or not. That is the first very vital starting point for any building. So now let us see that what are those architectural features which are either favorable or unfavorable as far as earthquake resistance is concerned. So first is the size of the building. If the building is too tall or it is too long or too large in plan, so basically any building with one of their overall sizes, it's much larger than the remaining sizes, then it might not perform well during earthquake. So here we can see that for this particular building, it is very large height to base ratio. In this, the building is not that high, but it is very long, right? And here the building is very large in plan area, like some kind of warehouse. So here we can see that you see that this is the too long building that has been damaged at the end part of the building. The second geometrical parameter is the horizontal layout of the building. Here we can see that these are the simple plans, the building with a simple plan. Here are the buildings with corners and curves. So the buildings with simple geometry and plan have performed well during strong earthquake. This is the past experience. Now, and building with re-entrant corners like U shape or the V shape, H shape, or the plus shape buildings, as shown in this figure, they have sustained significant damage. So, does it mean that we cannot build buildings with such kind of geometry in plan? No, it is not true. We can divide this complex geometry into this kind of regular geometry by providing seismic joints, seismic suppression joints. So this is basically a L-shaped building. We have provided a seismic suppression joint over here and divided into two rectangular parts, right? So each rectangular part is having a simple geometry and each part will behave individually during an earthquake, and the chances of their performing well are high as compared to the L-shaped buildings. So here we will see some few this real life examples of the buildings that we have designed while this provision of seismic suppression joints, right? So these are the examples of few of the building. Let us see those buildings. Now, this is the RK College of Engineering building. RK College is the RK University here in Rajkot, and this is the its engineering building. So this whole building is divided into 9 parts. Here, this magenta line shows the seismic suppression joint. So you can see that each and every part is divided into simple rectangle, right? Otherwise, what will happen that, and here also this provision of seismic suppression joint, there was an added advantage also. When the building was required to be constructed, as the starting this of the academic year was very near, it was required to complete the building very fast. So, provide this dividing the building in 9 parts by provision of seismic suppression joint help to construct each and every part individually while deploying more than one this construction team, and it was possible to this complete this large area within the stipulated time frame. So that way, this helped to achieve the earthquake resistance also for this each and individual part, and it also helped to complete the building well within the time frame. This is the new court building at Rajkot near this civil hospital. So here you can see the building was having this L shape, right? So it was divided into 3 parts by provision of this and this one horizontal and this one vertical seismic suppression joint, and the building was divided into 3 parts. This is the photograph of that building, and here you can see this line. This is the seismic suppression joint. It was 200 mm wide as per the design requirement. So this is the part 1, this is center is the part 2, and this is the part 3. And here you can see the seismic suppression joint. So functionally the building is continuous. Functionally you will not this feel that these 3 parts are separate. Functionally that is one building only, but as far as the performance during an earthquake is concerned, or as far as we are talking about when we are talking about it structurally, the building is divided into 3 parts. Now this is Hotel Fortune at Rajkot. This building has been divided into 2 parts. This one part central core and this surrounding is the second part. Now here what happened that this central part is a 2 basement plus ground floor plus 9-story building, this one. And this surrounding this part is a ramp structure going up to the ground floor only. So here we can see that this is the central part, and here you can see dual columns. Here you can see dual columns. So this column line is for part 2 of the building, that is on the outer periphery of the building, and this is the central core of the building, that is the part 1. So by providing a joint between 2 columns, so this column is for this particular part 1 of the building, and this column is for part 2 of the building. Here you can see that these are the bars for the part 2 column, and this is the part 1 column. Yes, this is the photograph of the same building. Here also you can see that the division of the building in parts help to execute the building as per the conveniency of the contractor. Here you can see that part 1, which goes up to 9th floor, was completed first, and this ramp structure was constructed later on as per the conveniency of the contractor, and it didn't require any kind of dowels or any kind of labs to be provided, because structure for both these parts is separate by provision of the seismic separation joint. This is the floor plan of Crystal Mall, Rajkot on Kalawad Road. Now here also you can see that this is geometry is very complex, right? If you have visited Crystal Mall, you will see that this is the front entry. This is the atrium, which is open, right? Or covered by only some steel, this glazing only. This is the central atrium, covered at roof, the roof level only by steel structure. And this is the main building. Now you can see that this is a U-shaped building, right, basically. So what was done, by provision of seismic separation joint, this building was also divided into 3 parts. So this is part 2, this is part 1, and this is part 3. Now we see that what happens when this seismic separation joint is not provided, and buildings having complex geometry are built while neglecting their geometrical parameters. Here you see that this was a U-shaped building, right? This being completely collapsed. Here this being completely collapsed, right? And very heavy damage at the corner. From the corner, these 2 wings have separated, right? Here also the photograph will show that this is a L-shaped building, irregular in plan, and heavy damage experienced at the corner. Here also we can see that this is a L-shaped building, and one wing is totally gone. Yeah, this building was a L-shaped school building in Ahmedabad, and orientation of columns in this longer wing, it was detrimental and resulted into complete collapse of the building. Here again, this is a building which H-shaped, right? H-shaped building in Ahmedabad. Now this building was having swimming pool at top level. So irregularity in mass, right? Very heavy mass was located at top of this particular wing, which resulted into twisting of that wing and resulted into total collapse of that particular wing, right? Now the third geometrical feature, architectural feature, is the vertical layout of the building. Now it is very important to have continuous load path along the height of the building for proper seismic performance of the building. Now any deviation or discontinuity in load transfer path results into poor performance of the building during an earthquake. Now here we can see that these are the buildings with setbacks, right? Here we can see that the floor area is large and suddenly there is a setback and the building reduces into a smaller plan area. Here also there is a setback at this level. Here a reverse setback, that the building is narrower at lower floors and it width increases at the upper floor. So building with vertical setback cause sudden rise in earthquake forces at the level of discontinuity. So at this particular level, the earthquake forces will suddenly rise, and it is very difficult to mathematically formulate those kind of sudden rise in the mathematical model, and very difficult to formulate, derive, and or it will require a very extensive efforts on part of a structural engineer to evaluate such kind of forces. Now, building with fewer columns or wall in a particular story or unusual tall story tend to initiate damage or collapse in that story. Here we can see that there is an open ground floor story building. So the upper part is very steep as compared to the lower one. In this building, this particular story is very high, unusually tall story. So its stiffness is less as compared to the upper stories. So, and as we saw during 2001 earthquake in Ahmedabad and Kutch, many buildings with open parking collapsed during 2001 earthquake. Similarly, building on sloping ground and tend to twist and may get damage. Similarly, buildings with floating columns, this is very dangerous. And for young structural engineers, it is very necessary to understand that this is a very risky phenomena and should be avoided as far as possible to go for the floating columns, because it results into discontinuity of the load path. The load coming from this column it requires to be distributed to the other columns, and this particular beam might not perform well during an earthquake and may result into the collapse of the wall building. Similarly, building walls with concrete walls not reaching up to ground are liable to get damage. Here we can see that there is a concrete wall, but it is not reaching up to the ground. So all the shear that has been extracted by this shear wall due to its high stiffness suddenly gets distributed to this slender slope, this small columns, and these columns might not be able to resist that heavy this shear transfer from this shear wall, and the building might get damaged. So let us see some of the examples. This is the open ground story kind of building. What will happen that when the earthquake lateral thrust occurs on this building, that upper stories are having infill walls and are very stiff. So that wall block will move as a one, and this particular flexible story will be attracting very heavy shear forces on columns, resulting into failure of columns. Here you can see that the damage at the upper floor is less as compared to that on the ground floor. Here also we can see that the open ground floor has totally gone. Again, this failure of column in open ground floor parking. Again, open ground floor failure, parking failure. Here we can see that the one side of columns get damaged in open ground floor due to twisting of the building. The building geometry was such that this part experienced the twisting in this manner, and this particular line of columns, wall line, got damaged. Here there was an open floor at intermediate level as compared to remaining floors. On all remaining floors there were walls, and those floors were stiff as compared to this one. So that particular open floor has gone and the remaining building is intact. Here the overturning of the building subsequent to open ground floor failure. Here we can see that when there is an unusual tall story, this becomes a flexible story, resulting into smaller stiffness. The wall upper part is intact, and here we can see that even the building is not complete yet. The bare frame has got damaged and almost collapsed due to this unusual, very high floor height of this particular ground floor story. Now there is the floating column failure. Here we can see. Now you see in earlier in Ahmedabad, even in Rajkot and other cities of Gujarat, there was a permission to cover the open balcony. So it was called covered balcony. So authority was allowing the people to cover the balcony at upper floor levels by paying some additional charges. So in architectural plan, it will be shown as a balcony which will be covered by extending the room wall at the edge of the balcony by paying some additional fees. So what will happen that on ground floor the column is here, right? Because the margin is required to be left as per the authority norms. So on ground floor the column is here, right? Now the balcony is covered. So there shall be a cantilever from this column, and on upper floor the column will be here. to cover the balcony, and as if this column will go continue like this, it will fall into room in between, right? So to avoid that, what people did, that here on ground floor the column was here by providing the sufficient margin, and on upper floor this column was shifted at the end of these brackets. So here we can see that this bracket supporting the floating column has gone. Similarly, this is also a failure of the beam with supporting floating columns. Here we can see that this is very heavy beam supporting these two columns, right? The building was having a heavy beam supporting these two columns. So this beam, right, was in something like this condition, that it was supporting a column, and when in case of an earthquake it was not possible for this beam to perform well and the building got collapsed. Here you can see this column bars starting from the beam. You see here also you can see that, these are this real life pictures from our cities only, Rajkot and Junagadh. Here you can see the number of columns on this lower floor and see the number of columns on this upper floor. You can see over here, this column has been erected over here, right? Here you can see that this column there is nothing here. Here also you can see that this particular column is starting from this floor, there is nothing below. So performance of such buildings during an earthquake shall always be questionable, and it is my appeal to young structural engineers that never do such kind of things during your practice, because it is very difficult to mathematically evaluate performance of such kind of buildings, and whatever you design, it is always be at doubt whether it will perform or not. So many a times it is asked that if the floating columns are not allowed, then is it true that we cannot design a very fancy buildings with larger openings at the lower floors and such kind of things? No, it is not true. It is possible. But you see, it should be done by very extensive structural analysis and design and very detailed dynamic analysis and nonlinear analysis of the building. Then only you can ascertain the performance of the building. Here you can see that this building is having only 4 columns at the ground level, and for this upper columns the load transfer is through this story high or 2-story high transfer girder. So this transfer girder supports this wall building and transfers the forces to these columns. Right, so the capacity of this transfer girder is required to be meticulously calculated, and then only we can provide such kind of things. Here also you can see that this kind of truss girder has been provided in this building to support the upper floors. Here also you can see that, right, the wall building is supported on this, but see the complete shear wall box has been provided to support this. So it is not like that it is not possible to design, but it requires very extensive efforts to design such kind of buildings. Now, one more feature is the adjacency of the buildings. When the two buildings are very close to each other, they might get pounded to each other during strong earthquake. Here you can see that in this top, the building is pounded to each other. So, as we saw, the architectural features which are not conducive for earthquake resistant design or are detrimental to earthquake response of the building, they should be avoided. And if not, at least they should be minimized. And when irregular features are included in the buildings, a considerably higher level of engineering efforts required on part of a structural engineer. And yet the building may not be as good as one with simple architectural features. So as I said, that this does not necessitate the buildings with monotonous architectural features. It is possible to design a very good aesthetically sound buildings, but if the input from structural engineers are received at earlier stage of architectural planning, then it will be possible to achieve a balance between desired architectural features as well as the structural requirements of the building. Now the next stage comes the structural design. So as we saw that the earthquake exerts lateral thrust and the twisting force on a building, right? So to achieve a earthquake resistant building, structural design calculations for lateral force and twisting effects are must. As a structural engineer, we cannot neglect those forces. So without considering those forces in design, it is not possible to achieve an earthquake resistant building. Here, these are few real life examples of the building movement during an earthquake and with a different kind of building geometry. Here we can see a triangular shaped buildings, and let us see how it will. Yeah. See, this is the movement of building in X direction. Now here you can see some twisting of the building, right? It is not moving parallel to the X axis of the building due to this exertion of forces in X direction. Now this is the movement of the building due to earthquake forces in the Y direction. Here we can see that as the building is more or less symmetrical about y-axis, it is moving parallel to the y-axis, and there is comparatively very less twisting of the buildings when we are talking about the earthquake forces in y direction. This is another building with regular geometry and with shear walls. This is the forces in X direction, earthquake forces in X direction. See that as compared to previous building, the twisting is very less, but it is there. And in Y direction, as the building is symmetrical, there is almost no twisting when the building is exposed to earthquake forces in Y direction. Now there is a dumbbell shaped high-rise building having a shear wall and moment resisting frame composite kind of structural system. And here let us see what happens. This is the earthquake force in X direction and moment of the building. See that though the building geometry is irregular, the structural components are arranged in such a manner that there is no twisting of the building when it is exerted to X direction forces. Similarly, when it is exerted to Y direction forces, you can see that only lateral movement is there and there is no twisting of the building. So by distributing your structural elements and by determining the sizes of your vertical elements, that is column and shear walls, in such a manner that the distribution of the stiffness is such that the building will move in horizontal direction only and it will not twist about the vertical axis. So this is one that these forces, lateral and twisting forces, should be considered in design. Then another okay,
please carry on.
So we will start from the structural part of this design part. So as we said that we need to design a building for the lateral thrust as well as the twisting effect. So we will start with this few real life examples when the building, how the building will behave in case of an earthquake. This is a triangular shaped building, and let us see that how it behaves during an earthquake. Is it visible? The animation is visible?
Yes, sir. The animations are visible.
Okay, fine. Now here you see that this is a triangular building which is unsymmetrical about x-axis, and here you can see when the x-axis earthquake forces are exerted, in addition to lateral force, the building twists. And as the building is symmetrical about y-axis, here we can see the only movement is the lateral movement and no twisting movement of the building. This is another building more or less the shear wall and moment resisting frame kind of structural system. Here we can see that how the building moves in case of an earthquake in the x direction. Here we can see that the building slightly rotates about x-axis, and when in case of an earthquake forces in y direction, the building more or less moves in horizontal direction only. This is another high-rise building with a small and moment resisting frame kind of a dual system, and the building is having an irregular dumbbell shape. So in case of an earthquake force, the building moves like this. And when we show in plan, here you can see that though the building is irregular in shape, the structural elements are proportioned such that the movement of the building is lateral only and no torsional movement is there in x as well as in y direction. Here also you can see that in y direction forces also the building moves in lateral direction only and no torsional movement. So it is very important to proportionate the vertical elements, that is shear wall and columns of the building, in such a manner that this twisting effect gets minimized. So the another concept is in addition to design the building for lateral as well as twisting forces, the next is the strong column weak beam design approach. So as we know that in case of an earthquake resistant building, there are possibilities that the building might get damaged, but the damage should be initiated from in the beam and not in the column, because we know when the column is gone, the safety of the wall building is at stake. So the damage should be initiated from the beams and not from the columns. So this is that theory that your columns should be strong as compared to your beams. And here the reverse case, the columns are weak as compared to beams. So this approach is a wrong approach, and we should design the building in such a manner that this plastic injuries or the damages is in beam and not in the column. So this is the strong column weak beam theory, and the building should not be designed like this, that your damage is initiated in the columns. This kind of damage gets initiated in case of an open story parking buildings. So the next stage, important stage, is the detailing stage. After the enough care has been taken during design, the detailing of the concrete building is equally important. So these all are the images which has been as per the rules given in IS 13920 and IS 456, that in beams this shear link should have 135-degree link, and it should be properly anchored inside the core. So the link should have the proper 135-degree hook. Horizontal spacing should be as per the norms and as per the IS code. Here also, that whatever the total amount of steel is required from the calculation in the beam center as well as on the support, that certain % of the steel as per the code should be continued in the remaining portion of the beam, right? Here you can see that for the 2D distance, D is the effective depth of the beam. So for 2D distance from the support, the stirrup spacing is closer as compared to the central part of the building. Here you can see the real life example, that you can see that near the columns, the stirrup spacing is closer as compared to the central part of the beam. So this is the ductile detailing of the beam as per IS 13920. Here you can see the column design and detailing. So for a column, this is the figure extracted from IS 13920. So same as for the beam, for the column portion near the supports, that is the upper floor and the lower floor, the tie spacing is closer. The lap of the vertical bar should be in this middle central portion of the column and not near the beams at either at the upper level or at the lower level. And these are the some rules that has been given in the IS 456 that this should be the at least larger of the this larger dimension of the column or height of the column by 6 or the 450 mm. Right, so these all dimensions are given in IS 13920, and while detailing of the columns, we should strictly follow this. And for columns also, this 135-degree hook of the ties is very essential, because here you can see that when this it's not provided in case of an earthquake, here you can see the tie has got opened, resulting into buckling of the vertical bars. Right, so this is the shear failure of the columns. Here you can see the standard detailing that should be adopted for columns. Here you can see the tie spacing is closer at the lowermost portion at uppermost portion of the column, and the laps are provided, lap for the vertical bar provided in the middle portion of the column, and those laps are also in a staggered manner. Here you can see the column detailing in the section that all the ties are with 135-degree hook. Here you can see that poor design and detailing of a column can result into this kind of situation. Here also you can see that this tie are not at the enough closer spacing and are not provided with 135-degree hook, resulting into shear failure of the column. Here also you see that 90-degree hook is there in the tie. Tie spacing is too large, right? And this 135-degree is missing. Here you can see that the lap length of the column bar is not enough, and the laps are provided at the slab level. So that is not desirable. The lap and the vertical bar should be in the middle portion of the column. Similarly, beam column junction is also very important as far as the detailing is concerned. That in beam column junction, this 135-degree ties should be provided in the column, in the junction for the column vertical bars, and also the beam bars, longitudinal bars should be properly anchored in the columns. So it should be almost development length of the bar, that is the requirement to that longitudinal bars of the beam should be anchored into the column. Here we can see that you see this is the column vertical bars, these are the beam horizontal bars, and you can see these ties, right? This is yet not properly binded. This is the completed junction. You can you can see the beam reinforcement. This is the beam reinforcement, and this vertical are the column reinforcement, and you can see the ties in the beam column junction, right? With this 135-degree hook. So this kind of standard detailing should be there. Here you can see that the beam bars are properly anchored in the columns, and beam column junction is having proper ties with 135-degree hook. So this is the standard detailing. And here you can see the beams are also having the 135-degree stirrups. So after architectural features and structural design, the next is the construction practices. So on site, we should adopt the standard quality structural materials, that is the design mix concrete, and it should not be nominal mix concrete. Then reinforcement with good quality with proper strength and the required ductility to perform during an earthquake. And periodical testing of concrete and reinforcement in standard laboratories should be mandatory. And proven practices to achieve the stringent quality control should be adopted. And then after concreting, that post-concreting care which is required, like curing and all those things, should be properly ensured. So here you see that one standard practice is to pour the concrete in columns from lower height. So why it is so? So normally that if the floor height is say 10 feet or 3 meter, then the beam column is required to be casted up to the beam bottom level. So that height shall be almost 2.5 meter or 2.75 meters. So if the concrete is poured from above, from that height, then what will happen? That due to segregation in this lower portion, the heavy aggregates, that is coarse aggregate, will reach at the bottom first, and they shall be covered with the cement and sand mortar slurry only. So at bottom level, there shall not be homogeneous mix that you prepared in the mixture if you poured the concrete from the top, right? So as the IS 456 says that the concrete should not be dropped from more than 1.2 to 1.5 meter height. So what we can do, that we can have a window in between, first to pour the concrete from this level, and when the column up to this level has been casted, this window can be closed and the remaining portion can be casted while pouring the concrete from the top. Now here you can see that if the concrete is poured from the top, what can happen? In the failure of this particular column, what was found was dry coarse aggregate in this junction covered by cement slurry only. So there was actually no concrete, only dry this coarse aggregates were there in the inner core of the column. And when the column shuttering is open, it will look fine because the dry aggregates are covered by the cement slurry. So from visible inspection, it will not be possible to see whether the this core is having the proper mixed concrete or not. So it is very important that the concrete is not poured in the column shuttering from very large heights. Here you can see that, see this window is here. So this kind of hopper has been formed. So first the concrete shall be poured from this lower height. It shall be get vibrated from the top while inserting the needle from the top. And once the column has been casted up to this level, this window shall be closed and the remaining concrete shall be casted from the top. Then proper curing of fresh concrete at least for 7 days. So this is also very important, that if you have taken enough care in design, detailing, concreting, material, everything, but if you miss out on curing of the concrete, then all your efforts are in vain. You see, this method of curing for slab is very essential. Then the next stakeholders comes are the local authority policies. The building bylaws or the GDCR can play a very major role in guiding the current practices to have a good or poor lot of buildings in context of their earthquake resistance. As I said that earlier, it was permissible to have a covered balcony. So here you can see that all these columns are at lower level inside with the required margin. And from these brackets, the remaining columns will be at this edge. So this is detrimental as far as earthquake resistance of the building is concerned. So desirable initiatives from local authorities is to allow construction of walls at ground floor parking to reduce effects of open ground story. This is very important. If you, when we are providing the open ground floor parking, so it is necessary that we cannot close the parking by providing all the walls. But on the periphery, if judiciously certain walls are provided in such a manner that those walls will act as shear walls, and it will reduce the effect of open this ground floor parking effect, which is detrimental for the building in case of an earthquake. And for buildings with floating columns or unusually high story, it should be made mandatory to proof check the design, structural design for such kind of buildings. And it should be decided to have a proper this important index of various category of buildings, and for buildings beyond certain importance index to make the structural design proof checking mandatory. These are certain desirable initiatives from the local authorities, which if adopted can definitely help to make this this construction livestock most of the buildings as earthquake resistant. So these are some acknowledgement of the data which has been taken in this presentation, and it was prepared by Lakhlani Associates. So thank you, friends, and I hope that I was able to convey this desired this intent of this presentation, and I would welcome if any questions are there from any of the participants.
Yes, sir. Good afternoon, sir. This is Ankur Bhogaita.
Good afternoon, Ankur.
Yes, sir. It was as usual. It was amazing, and your presentation was worth watching. And I am sure that all the participants must have got the insights what you have delivered to them. Sir, we have a few questions here.
Yes, please.
So, with your permission.
Yes, please. Yes, please. Please go ahead.
Yes, sir. Actually, somehow that text is not readable to me. So we will do one thing, sir. We'll get back to you with the questions through the email from the questioners.
Okay.
Because somehow the text is not readable.
Okay.
So not an issue. The participants are encouraged to send their questions directly to our official email addresses, and we will get back to it through the help of the expert with us today. So, sir, we would like to thank you for your precious time and sharing your knowledge with us, sir. And I'm sure that, as usual, we shall be again get connected for the future similar kind of activities, right, sir?
Yeah. My pleasure. My pleasure.
Yes,
thank you.
yes.
Thank you very much.
Yes, sir. So on behalf of Marwadi University, the Department of Civil Engineering, and the Atal Academic, that is the new initiative by AICT, central government. So we collectively are thankful to Mr. Jayant Lakhlani, sir, for being with us today. So thank you, sir, once again, and have a nice day ahead, sir.
Thank you. Thank you, Ankur. Same to you.
Yes. Yes, sir. Thank you. Okay, sir.
Yes, thank you, sir.
Thank you.
Yes, and for the participants, we have few announcements. Your online MCQ examination that is scheduled at 2:50 p.m. today. It will be 40 minutes exam. We'll be sharing you a Google form in which you have to respond within 40 minutes. And the total marks are 30. 30 questions will be there, and total time is 40 minutes. And we will close this Google form exactly at 3:30. We will float it at 2:45. Some may take to join or refer by 5 minutes. So additional 5 minutes for the net connectivity that we have kept. Otherwise, effective time is 40 minutes. And after that, subsequently, we will have our valedictory session at 3:45 p.m. So all are requested to join. We will share the link for the valedictory. All are requested to join in time. And further instruction which are related to the completion of this FDP and your certification, that we will discuss at the time of valedictory. So with this, we end the session here. So thank you once again. And
thank you, Tara.
Yeah, thank you, sir.
Thank you. Thank you, Tara. Have a nice day. Bye-bye.
Have a nice day, sir. Yes.